And today we're going to talk about one of the most legendary mechanisms in DeFi, which is the automated market maker. It is one of the most powerful inventions in DeFi, the kind that helped turn smart contracts into full-blown financial applications. I know AMM sounds very fancy, but by the end of this video, you will not only know what AMM is, but you will be able to build one. Everyone, I am Sneha from the Web3 Compass, and this is day 25 of 30 days of building with Solidity. For everyone who is not aware about this campaign, you can head over to my day one video. That is where I talk about the entire program in detail. Or you can go over to web3compass.xyz and find the entire challenge calendar here. Now, I'm so happy that we're finally very close to the campaign, and although the motive was to turn one complex concept into Solidity code every day, so over 30 days, we're going to write 30 smart contracts, but we finally covered most of the concepts and we're diving into real world applications already. And today we're going to talk about one of the most legendary mechanisms in DeFi, which is the automated market maker. It is one of the most powerful inventions in DeFi, the kind that helped turn smart contracts into full-blown financial applications. I know AMM sounds very fancy, but by the end of this video, you will not only know what AMM is, but you will be able to build one. Okay. Now, before we start with code, I know you guys are very excited. We should first understand that why did people come up with the idea of AMMs or started using it? And this goes back to the time when, crypto was very new and trading happened just like how stock market works. So you had buyers who said, hey, I want to buy one DAI for, 0.95 ETH. Or you had sellers who would say that I have one DAI to sell, but I would take 1 ETH for it. And sitting in the middle of all of this was a system called order book, thinking of it like a giant list, which was matching buyers and sellers. So when a buyer and seller both agreed on a price, boom, the trade happened. So this system works great on centralized exchanges like Binance, Coinbase, but then there's a problem. Okay. On blockchain, everything costs gas. Even something as simple as, hey, I want one DAI, which means sending a transaction, paying a fee, waiting for it to confirm. Now imagine every time you wanted a tiny change to buy or sell price, you would have to pay something, right? And what if no one wants to trade with you at the moment? You're stuck. Your order just sits there, wasting gas and time. So here was the core issue. Order books were centralized. They need people to be active all the time, and they're slow and expensive to use on chain. So DeFi needed something way better than this, right? And that is where this breakthrough came in, that what if we do not need buyers and sellers? What if a smart contract could just act like a vending machine for tokens? So instead of relying on people to trade with, you would have a pool of 2 tokens like DAI and ETH logged in a smart contract that anyone can use. Want to buy ETH with DAI? The contract does the math, gives you ETH, keeps your DAI. Want to sell ETH for DAI? Same thing. The contract gives you DAI and stores your ETH. So no need for buyers, no need for sellers, just math. So with AMMs, it works on a very simple formula called X into Y equals to K. Now, X you can assume as amount of token A in the pool, and Y you can assume as amount of token B in the pool. K is some constant number which never changes. So the product of the 2 token reserves must always stay the same. So here's the magic that happens. If someone wants to add more of token A like ETH, the only way to keep K constant in this equation is for the contract to give them less of token B like DAI. Okay, that's how prices adjust automatically. And as people trade more and more, the ratio shifts and the price updates on its own. That is why it's called an automated market maker. The contract makes the market using math, not human orders. Okay. Now, what is it that you can do with AMMs? You can swap tokens where you can instantly trade token A for token B, vice versa. No need to wait for a match. Just send the token, get the other back. Add liquidity where you deposit equal value of token A and token B, and you get a liquidity pool to tokens like a receipt. You earn a cut of trading fees maybe while your tokens are in the pool, and remove liquidity like return your liquidity pool tokens, get your share of both the tokens back, etc. Right? Now that you've gotten the idea, in the next section, we will look into writing Solidity contract, where we'll show how the liquidity pool works, how the price math is calculated, how to make sure everything stays fair and balanced. We're not using libraries, shortcuts, behind the scenes magic. Everything will just be straight away code. Now, just a disclaimer, we're going to write 3 smart contracts here. One is the main AMM.sol, and the other 2 would be the token contracts for token A and token B. But then you don't have to worry about it because these will be written using Open Zeppelin's framework or ERC20 framework. So it's just tiny bit of contract and you just have to make a minor change. We have already talked about implementing ERC20 in detail on one of our days. So you can go back, look at that video if you're not aware of what ERC20 is. And yeah, I mean, we can get started, right? Now it's time that you understand that how you are going to create liquidity between 2 ERC20 tokens, how users can add and remove liquidity, how to keep track and update internal resources of reserve A token, reserve B token, allow anyone to swap token A from token B, see how the formula X into Y equals to K is working, issue custom LP tokens here where it represents the ownership stake in the pool. If the pool grows because of trading fees, the LPs benefit because they can withdraw more than they've actually put in and all of that. So basically, you're recreating the fundamental building blocks of a decentralized exchange, the kind that runs on Ethereum without any humans, brokers, or middlemen. And yeah, you're going to write it line by line, fully transparent, decentralized, fully under your control. So let's just get building. Oh, here is some information. System for trading tokens automatically. You will learn how to create liquidity pools, everything that I've talked about. So let's just head over to Remix. We will create all our files right now. So the first one is AMM.sol. Okay. The other 2 would be token A.sol and token B dots, right? Great. So these are the 3 files that we're gonna work on all together. As I mentioned, token A and token B would be ERC20 tokens using the Open Zeppelin's framework. So you don't have to really worry about it. And yep, that's pretty much it. So let's just copy it from, okay. Let me zoom in. I think this is fine. I will close this. Should be, yeah. So we will copy this. Okay. Now, we know that we have to import the Open Zeppelin ERC20 framework and then how we have to, inherit in this one for the AMM to actually use those token contracts as well. So I'll just quickly copy the link. Okay, great. So this is the import that we use. We are basically importing the ERC20 contract from Open Zeppelin. Again, we've talked about Open Zeppelin ERC20 in very, very much detail. So we will not talk about it more in this video, and let's get started. Contract automated market is. ERC20. Now, everybody knows that here is basically inheriting the entire thing and saying that, hey, we're going to deal with ERC20 tokens. So this is going to be the brain of our entire application that we are building. The rest two are just simple token contracts. Now, though we are inheriting ERC20, we're basically saying, hey, Solidity, my contract should behave just like an ERC20 token. And on top of that, I will add some extra AMM specific logic. So the question is also, why does AMM need its own token? So every time someone provides a liquidity, we give them a token to represent their share in the pool. That's the liquidity pool token. It behaves just like any other ERC20 token. It can be transferred, tracked, and later redeemed for the cut of the pool. So this line is more like a declaration that we are doing. And now we will move forward to state variables and we'll see what we're trying to do. So the first thing that we're writing here is IERC20 public token A. Now the similar would be for B. These two basically holds the address of the ERC20 tokens that the AMM will manage. They're typed in as IERC20, which is just an interface and a way of saying that, hey, this thing behaves like an ERC20 token. So I know it has transfer from, approve, and other ERC20 functions. So if the AMM is using DAI and ETH, then token A might be DAI, token B might be, ETH or USDC or whatsoever. Okay, yeah. Now, why are we making it public? Because we want these to be viewable from outside for front ends, explorers, or other contracts in general. Now we will declare the resolve. So we will say uint 256. uint 256 public reserve A. And the same would go for reserve B, right? So these two numbers track how much of each token is currently logged inside the AMM contract. Why do we need this? Again, the entire AMM logic is swapped, prices, LP shares, depending on knowing how much each token is in the pool. So that is why we need to have an idea of, how much each of these contracts is, like reserve is. Okay. Now we say address public owner. Now, this person is the one who deploys the contract, adds governance, maybe let the owner pause swaps in an emergency, introduce a fee switch later, etc., etc. Yeah, that's pretty much it when it comes to, adding the state variables. Now let's just get writing some events. So we're saying liquidity added, and we would say, okay, we need the address of the provider, whosoever is providing it. Then we need amount of A, then we need amount of B, and then we will need the amount of total liquidity that we have here. Okay, so this is one event that we're saying. Again, all of these events are very, very useful when you're working with front end. Now, similarly, we will have liquidity removed. Actually, I'll just copy this entire thing because this is exactly what we need, right? Who was the provider? What was the amount of A? What was the amount of B? What is the liquidity, etc. Now, there would be one event which talks about token swapped. Okay. Now, address of the trader, right? Address of the token which is which is being swapped, address of what is the amount we're looking at, then address of the token that is going out, right? Because all of these tokens would be deployed and they will have their own contract addresses. And then there would be an amount that goes out, right? You have to maintain the ratio here. So, okay. So probably these are very, very liquidity added. Yeah. So these are very, very simple events where we're saying for the first one, he said, who added the liquidity? Like who's the provider here? How much of token A and token B was added? How many LP tokens they get in return? Similarly for liquidity removed. Now for tokens swapped, who did the swap, what token they gave in, that is our address token in, how much did they give in, right? And then what token they got out, and then how much did they receive. Now this is UNT 256, sorry, right? For example, we can say you swapped 10 DAI for 9.87 USDC, right? So we would need the address of DAI, USDC, and then the amount of each one of it. So that is where it comes in the picture. Now let's get to writing the constructor. Okay, constructor. So what we do here is that we take address of token A because, oh, where have I written it? Sorry, guys. Address of token A, right? Then address token B, right? Then we say string memory name. Now, this name is going to be the name of the liquidity token that we're going to create, like for the pools, and then string memory and symbol. Okay, and since we are using ERC20, this is how it works. We have seen this before. In case you haven't, please go to our previous videos. Yeah, the symbol. So the one that we'll create here, that their symbol will be added. So we're saying token A is equals to IERC20 and then underscore token A. Similarly, for token B, right? Great. And then we say, hey, the owner is basically the message dot sender. Now you can make this a little complicated by adding features like you are checking that token A is not the same address as token B's address, and that it's not a zero address and all of that. So, yeah, I mean, you can do that on your own. Here, we don't think that it was really, really required. That is why we didn't add it. And then for when we are setting up this through this line that token A is equals to IERC20 token A, then we're basically passing the two addresses and treat them as ERC20 tokens using the IERC20 interface, right? That's pretty much it. Now, we'll write some helper functions, some small tools which have like a bigger purpose later on. So let's just get started. We're saying function min, and we're saying uint 256a, uint 256b. This will be an internal function, pure returns, and then we say uint 256. Now this itself suggests that what is it that you need? A minimum of both, right? So we'll just use a ternary operator here, put a question mark. Which one should you return in this? Right. Correct. So this was one cute little function. The other one would be a square root. So we say uint 256y. Now again, we've done something similar before for the calculator function where we were calculating the power in square root. Returns uint 256c. Okay. So here, basically what we say, hey, if y is greater than 3, right? What? Oops. if y is greater than 3, then what you have to do is substitute z as y, and then you take another one which says u int 256x is equals to y by 2 plus 1. Again, I think it's called the Newton method, where we just do a half and go about it. And while, okay, x is less than z here, or z, whatever you pronounce, you substitute z as x, and then x should be equals to y by x plus x, and the entire thing by 2. Okay, this is one thing. Now you have to go with an else if condition. Else if y is not equals to 0, just put z equals to 1. Okay, that's it. That's all that we're doing here as square root calculation. Now you can do a dry run and then just look into it. Now, why do we need these two is that for the minimum function, we are going to further write a function called add liquidity. So when someone is adding tokens to an existing pool, we want to mint LP tokens based on whichever token amount would contribute less to the pool to keep the ratio stable and prevent over minting. So if the user sends, suppose 100A and 150B, we will use 100A and only 100B worth of tokens to mint LP tokens and return the extra 50B to the pool unused. So the minimum function basically keeps a track and making sure that the things are balanced and fair. For square root, this is the Babylonian algorithm for calculating the square root of number in Solidity. Now, when we're going to write the add liquidity function again, the very first liquidity provider gets LP tokens equals to the square root of amount A into amount B. So this ensures that the LP token supply starts at a very balanced value. It reflects the geometric mean of the two tokens added. So even if you've added 100A and 400B, your LP tokens will be based on square root of 100 into 400 rather than just the raw sum of it. So it's fair, math driven. So why do we have to put these in contract? It's like small pure functions, no storage, no read write happening. They're used internally to keep your logic very, very clean, and they help prevent bugs as well, especially when you're dealing with token math where fairness is very, very important. So that is why we have added it in the contract. Now we'll get to implementing some real useful functions. So let's say function add liquidity, right? We say uint 256 amount A, right? And then we say uint 256 amount B. Okay. We will make this external. There is a condition check required which says amount of A has to be greater than 0 and also amount of B has to be greater than 0, right? If yes, great. Otherwise, both amount should be more than 0. Okay. That is one condition that we're checking. Now what we will do is do a simple transfer, token.a transfer from. Again, this is already implemented when we're using ERC20 message.sender, and then address this in amount. This and then amount A. Okay. Similarly, we will do a token transfer from B. Oh, so we will say token B, again, message.sender, address this, and then amount B. Okay, great. Now what happens is uint 256, let's declare a liquidity variable and see certain things. So we will check if total supply, right? We have not implemented this. We say if total supply is equals to 0, liquidity is square root of amount A into amount B, just like we talked right now. Okay, this is the starting of it. Otherwise, else liquidity would use the minimum, which says minimum. Okay, amount of A into God, total supply divided by reserve of A. Okay, and then similarly amount B into total supply divided by reserve B. We don't need this here. Okay, reserve A, reserve B, there would be a comma here. So we're choosing the minimum one. Okay, and then we're saying it's time that you mint the liquidity pool tokens as many numbers. So if you have followed us through the ERC20 contract, then you know that where this mint function comes in and the address and the initial supply or the total supply. And then what we will do is we will say reserve of A plus equals to amount A. Similarly, reserve of B plus equals to amount B. And then we emit an event liquidity added. So who's the provider? Message dot sender. Amount A, amount B, liquidity. Everything remains the same. Right? So this is pretty much it. Again, very, very clear-cut implementation that the function lets user add liquidity to the pool by depositing equal value amounts of token A and token B. In return, the user receives LP tokens, which represent their share in the pool, right? And again, these LP tokens are like a receipt, proof that you contributed to the pool and claim your share of tokens to it. Both the tokens should have a value, or the amount that you're providing should have a value greater than 0. Now, then what happens is that you're doing a transfer here. So we use transfer from because the user needs to approve the contract to take their tokens first. A very standard ERC20 behavior. We have talked a lot about it in detail in the ERC20 implementation, and the approve function must be called, right? And then we are checking that in the next section where we are deciding liquidity, we're saying, hey, how many LP tokens should we give to the user? So if they're the first person ever to add liquidity, there's no liquidity pool tokens apply yet. So we give them a square root of amount A into amount B. Again, very standard formula by Uniswap to give a fair starting point. If the pool already has liquidity, we calculate how much they should get based on the proportion contribution. We make sure that the user adds liquidity in the correct ratio. So we use minimum to avoid over minting LP tokens if the user's amounts are slightly off. And then we mint the LP tokens again, underscore mint complete ERC20 function, inbuilt function that we're talking about. And then we update the internal state of the contract to reflect that the new tokens have been added. And this is very important because the swap that we might go do later depends on these values being very, very accurate. And then, you emit the liquidity added. Again, this logs in an action in the front end, and dApps can just show users what just happened, right? Now, we will write something called as remove liquidity. Okay. Function remove liquidity again. Uint 256 liquidity to remove, right? Just one amount. external returns UN 256 again, an amount A that is out and then amount B that is out. Okay, this is what we're going to get out. So again, the first required condition would be liquidity to remove has to be greater than 0, must be greater than 0, right? And then the other thing is that you have to check the balance of message.sender has to be greater than equals to liquidity to remove, right? So we say require balance of message.sender greater than equals to liquidity to remove. Okay. If yes, great. Otherwise, insufficient amount. Great. Right. Now you will say, hey, the okay, yeah, we're still writing. Sorry. So we say UN 256 total liquidity has to be equals to total supply, right? So we also need to require that total liquidity is greater than 0. Otherwise, we will say no liquidity in the pool, right? What else now? Okay, we want out, right? So we say amount A out is equals to liquidity to remove, not reserve B, A, right? By total liquidity. That's how we're making a fair proportion, right? Similarly, for B, we say amount B out. So liquidity to remove into reserve B by total liquidity, right? Now, again, the conditions also have to be that amount A out has to be greater than 0 and amount B out has to be greater than 0. Otherwise, we will say insufficient reserves for requested liquidity. Right? So both of these have to be like a valid amount that we're talking about, right? Now, once we've checked these, we will just pick up one reserve and we will be amount A out. Similarly for B. So we say reserve B minus amount of B out, right? And this is where we burn the tokens. Again, we have not talked about this in ERC20, but once you understand the implementation of ERC20, you can read more about burn and how we're destroying tokens here because it is no longer required. And then we say, hey, token A dot transfer message dot sender and the amount A out. God, what have I written? Right? And then similarly, this would go for token B as well. So we say token B dot transfer amount B out, right? because we have to remove the liquidity pool tokens corresponding to the amount that we are taking out, right? And then we say emit liquidity removed, provider message dot sender. Amount A is amount A out, B out. And for liquidity, it's liquidity to remove. And what you will do is just return amount A out and amount B out. Yeah, that is what we wanted as a return type. Very, very simple in explanation. Everything is very, very simply put, that this function will let user withdraw their share of tokens that they have previously added. They do that, they give back or burn their liquidity pool tokens, and in return the contract gives them a proportionate amount of token A as well as a proportionate amount of token B. Everything is based on their share of total liquidity pool. If they owned 10% of LP tokens, they will get 10% of each token in the pool. So it's pretty much understanding. You check both the required condition where liquidity to remove has to be greater than 0. The balance has to be there so that we can confirm that this particular message dot sender actually owns enough LP tokens to do so. Then you're checking the total supply of LP tokens. That should be like 100% ownership of the pool. If for some reason it's 0, we prevent the transaction. That means there's no liquidity to redeem from. Again, amount A out and amount B out is where the magic happens. We use a very simple proportion to calculate how much of each token the user should get back. So their liquidity pool share into their total token reserve is equals to, the withdrawal. So if they own 25% of liquid pool tokens, they get 25% of both token A and token B in the pool, right? And just in case we get some dust values due to rounding, we reject if either output would be 0 to prove, to reject any kind of or prevent any kind of broken or wasteful withdrawals. That is why we're checking the condition that amount A out has to be greater than 0 as well as amount B out has to be greater than 0. And then once everything is done, we just subtract the withdrawn amounts from the internal record of reserves to keep our swap math very accurate, because again, every trade is relying on these reserves being correct. Now, if the user is returning their LP tokens in exchange of the real tokens, we burn them, effectively deleting them from existence so that there's no double dipping that's happening here. And then we just transfer the token A and token B to the message dot sender and then emit the event. Very, very simple, right? Now, what we will do is write a very cute function, which is function swap A for B. And we say uint 256 amount A in, and then uint 256 minimum amount of B out. Okay. And this is going to be an external. Now, again, we're basically going to swap token A for token B, which is swapping maybe DAI for ETH or ETH for DAI or USDC whatsoever. We will check require amount A in has to be greater than 0. Amount must be greater than 0 here. And then there should be a require condition that checks what is the reserve of A, reserve of B, and that both should be greater than 0. So we're saying reserve A greater than 0. Sorry. And reserve B is greater than 0. And it says insufficient reserves in case it is not. Okay, now what we do is there would be obviously a fee that will also be charged here. So we say uint 256 amount A in with fee. Okay, so we're saying amount A in into 997 divided by 1000. Now, what we're doing here is that because we have to maintain a certain ratio, we're cutting like 3% of it. So if you send 100 token A, only 99.7 gets used for swap math. The remaining 0.3 stays in the pool as a reward for liquidity providers. So we're basically not applying 3%, we're applying 0.3% fee here. Okay. For the liquidity pool providers, amount B out is equals to, you will check the reserve of B into amount of A in with fee, because corresponding like 100 DAI is equals to 50 ETH, right? So whatever number of ETH or DAI that you give swapping, you have to calculate it with that. So we will check the reserve of A. We'll check how much amount of A in with fee is actually calculated, and then divide this entire thing with reserve of A plus amount of A in with fee. Okay. And then we check a condition where we say, hey, is amount of B out that we are declaring greater than equals to whatever min B out that we provided as a parameter? If yes, great. Otherwise, there's a slippage too high. That means that we are losing like tokens, or it's just not enough. Okay, so it's like you are we're calculating how much token B the user should get from the amount of token A that they're putting in. Now, reserve A was how much token A the pool had before the swap. Amount A in with fee is the new token A being added after applying the fee. And then we have to make sure that the formula is still into practice, x into y equals to k. So the more you add to the pool, the less you get per unit because it pushes the ratio. This is called price slippage. So it's fair, it's automatic, and it doesn't need any such humans to be involved. So we check that if the actual output is at least what the user expected, because the user has said minimum B out, it will only do this swap if I get at least X token for token B, right? If the math gives them less than that, we revert the trade to protect them from unexpected price movements. Like the person has a certain expectation, and if the value is less than that, then we are like, that means like the slippage is too hard and we don't want to go forward with the trade. Okay, now once we've checked all of this, we say token A dot transfer from message dot sender address this, and then we say amount in, right? Amount in. Okay, great. Now similarly, token B dot transfer. Now that was a transfer. That was a transfer from, this is a transfer, and we say message sender amount B out. Okay. Now what we're doing is we will add the reserve A plus equals to amount A in with fee, and then reserve B minus equals to amount B out. Okay, and then we just emit token swap. Okay, so the trader is message dot sender. The token in is basically address of token A. Amount in is amount in. The token out is address of token B. and then amount B out. This will be A in. Now, this is somewhere where I was very confused when I was working on this one, that, hey, when I am doing the transfer token and we're saying that we want to swap A for B, shouldn't A's price or A's amount be the one subtracting, and the reserve of B should be the one that is increasing, right? But then what happens is that the logic updates like this, that what was it again? Yeah. So we will increase the reserve of A because we received more token of A, and we will decrease the reserve of B because we give away some of token B. That is how the current, accounting for AMM works. When a user swaps token, the pool's reserve of the input token increases and the reserve of the output token decreases. Okay, that is why here A will increase and B will decrease. So I was lost here for a really long time. And while we are updating the contracts record of how much each token it's hold, there could be a question that why do we only add amount A in with fee to reserve A? Because the fee portion does not really count towards the swap logic. It's not available for the next, trader. Okay. That is why, yeah, just that addition. Now, token swapped emit goes really, really well. Now, this similar function will be written for B for A, and we'll make a few changes here. So we say B for A, okay, and this will be obviously B in, and then this will be minimum A out. Again, this will be B in, amount must be greater than 0. The reserves of both will be checked. For here, it would be B in with fee, then it says amount B in into 997 divided by 1000. Amount of A out that we're going to get will be reserve of A, and then reserve of B in with fee by reserve of B. It works the other way around. So if I've explained the first thing, I don't think we need an explanation here. So we just replace everything very quickly. We're transferring this, okay, and this one would be just transfer. So here it's amount A out, right? And here it's amount B in. But what we've done here is, I don't think we've written A here, so A in, right? And then we're saying, okay, now this one would be reserve of B is amount B in with fee, and reserve of A is minus equals to amount A out, and then emit token swapped. This should be token B, this should be token A, this should be B again, and this should be A out. Great. This is the mirror of swap A for B. It allows user to swap token B into the pool and receive token A in return, following the same pricing logic, same constant product formula, same 0.3% fee, and all of that. That is why those calculations. Now, what else are we left with? I want to write some utility function where we'll be like, let's just be able to get some reserves. See how much of the reserves do we have for, both of them. Function get reserves. And we're saying external view returns. And there are two tokens. So UINT 256, UINT 256. Okay. Return reserve A, comma, reserve box. Yeah. Great. So then again, expose the current state of the pool, how much of token A, token B the contract is currently holding, doesn't change anything, doesn't cause gas, so just works well for it, well for us. Now what? Okay, it's time that we check our contract, like deploy it and check. But before that, we have to quickly write this token A dot sol. I have just copy pasted it. I've explained this before, so I don't think you should have an issue. Somewhere it's showing an error. Oh, did I not write event here? Yeah, that should be fine now. Where? Oh, yeah, A. Sorry, guys. Yeah, it's all cool. Okay, so token A looks like this. Similarly, there would be a token B. Okay, I had it written. Okay, so I'll compile token B, I'll compile token A. Now we go to deploying. So we deploy token A, then we deploy token B as well. And then when we come for AMMs here, it would need the address of token A. So we will just copy token A here, paste it. We'll copy token B here, paste it. For here, we will write liquidity pool token, and we will give the string as LPT. Okay, and transact. So here we have the automated market maker. Okay, this is token A. Again, it has the ERC20 thing, the total supply we've set already, name, symbol, blah, blah, blah. Great. So we need to work here. Token A, contract. Token B, contract. Total supply right now, 0. Symbol LPT. Reserve B, 0. Reserve A, 0. I am the owner. Liquidity pool token. Get reserve 0, 0. Okay. So now let us just add a liquidity here. Now you have to be very mindful that if you're adding like 1,000 tokens here, then you have to give 1,000 plus assuming that it's 18 tokens extra. Okay, so what you have to do is before you add this liquidity, you have to go here, okay, and you have to give the value of the spender, which is the AMM here. So you will have to approve that, and I'll paste it here. So if you count, this will be 21 zeros altogether because it's 1,000 tokens that we are approving. And I will just quickly copy the automated market maker's address and just transact it. And if I show you here, what happened here is address spender value pool true. So there's an event approval, again, predefined and this and that. Similarly, we would do this for token B as well. That is how we get the permission to, add these. Second. Transact. Okay, so we've done this. Let me close this one. Let me close this one. Now here, okay, yes, add liquidity, right? So now in this add liquidity, what you're going to do is you have to add amount A as well as amount of B. Now, example, we want to just add 100 of both the tokens for token A, token B. So we will just add it with 18 zeros. So these will be 20 zeros. Now, if you check get reserves, this is equal. If you wanted to add like more of it, see what happened here is that address that may be allowed to operate without being their owner amount is allowed to operate with needed maximum amount required to perform a transfer. So it says insufficient allowance that we're talking about. So that is how it will, show you an error. Okay, so now you've officially added liquidity here. You will see LP tokens, which is minted to our address. So if we check the balance of, yeah, so this is the amount again. If we do a square root of 100 and then 100 with those many zeros, that is what we're going to get, right? Now, if you want to swap A for B, if that is what you want to try. So suppose we say, okay, we want to swap 10 A tokens, okay, for, we'll paste it here, we'll remove 1 0 and we're doing a 5 here, so it's like half B tokens, right? Right now, get reserves, both are like same. Now, when I perform this, okay, you will check that the reserves for A will increase and the reserves for B will decrease. Again, that is how AMMs work. Whatever is added more, the reserve will increase there, and the next one to maintain a constant. Again, get balance of, fine, reserve of B, reserve of A, total supply. This is the total supply here in the liquidity pool. Okay. If we want to remove liquidity, let's just remove the entire. Let's try this. So you can do similarly. Okay, now if you check, total supply is 0, get reserves, both are 0. So yeah, that's how it totally works. Now you can do a reverse swap, you can remove liquidity, which we already did. So you will get your share of token A and token B's address back. The total supply, the balance of this one. So a little less, some percentage cut happening here. And this is like maintained. Okay. So yeah, all of these events will be also visible, liquidity added, token swapped, etc. So yeah, that was pretty much it. You deployed a 2 ERC20 tokens, built and tested your own AMM, swapped tokens using math instead of market makers, and became the first liquidity provider to your own DEX, right? So you've learned the core of AMMs, wrote a full smart contract logic around it, ran it in Remix. So great. So you now not just understand how AMM works, but how actually you can build one. And I will see you on day 26. Till then, keep building, guys.